Hello people and welcome back to another video. In this video, we'll be continuing from where we left the last time in our first lecture. If you haven't watched that, I will highly recommend you all to go back to the first lecture and watch that lecture where I introduced you all to some of the fundamental mathematical concepts which are important to machine learning. I gave a brief overview in that particular lecture. Here we are going to be continuing from that lecture and we'll be studying one of the key distributions which is extremely important in the field of statistics. That distribution is the normal distribution, or what mathematicians and statisticians often like to call it the bell curve. Now, firstly, let me make you understand why in the first place the normal distribution is held in such utmost importance in the field of statistics. So, a lot of statisticians did this research where they analyzed a lot of real world population data sets and they tried to depict those data sets in a histogram. What they found out was that in majority of the scenarios, when the histogram was plotted against these population data sets, majority of the data lied between 2 points which were briefly at the center of the curve. So if I had to demonstrate that, let me pull out my pen. Let us suppose I'm plotting the histogram of the population set. So what researchers found was that most of the data lied somewhere here. So it was something like this. I would also like to say that this is a rough diagram. In reality, the histogram was plotted using technology. So the real diagram would be much more accurate than this one. But you get the general idea. It was somewhat like this. And the the frequency starts to decrease as we move forward along the left and the right. So this is where majority of the data lied. And so if one has to make an outline on this particular curve, it will go somewhat like this. It will have a peak at the center and it will come down after that. So if I have to draw this outline separately from the histogram, it will look something like this. It will start to increase, then then it'll hit a singular peak point, and then from there it will start decreasing. Somewhat like this. So this particular distribution is referred to as the normal distribution or also referred to as the bell curve. Now, the equation of the bell curve is given by this particular equation. F of x is given by 1 upon sigma root of 2 pi exponential raised to the power of minus 1 by 2 into x minus mu upon sigma whole square. Now, in the previous lecture, if you have watched that lecture, you know that sigma here represents the standard deviation and mu here represents the mean. These are some of the fundamental notations in statistics that is used very frequently. So all in all, what they're trying to say is that if I pick a point on the curve, let us suppose this particular point right here, if this is my x and this point right here, this is my f of x, then my f of x is given by this particular formula. So from the formula itself, you can clearly see that the normal distribution is a distribution which is driven by the mean and the standard deviation. Now, often what happens is that we find multiple curves in our real world data sets. And because these curves are driven by mean and standard deviation, we'll look into these two aspects in a little more detail. Now, in a normal curve, what does the mean represent and what does the standard deviation represent? Now, the mean, obviously, as we have studied previously, is an indicator of the central value. So the peak of this particular curve, the x coordinate of that peak is fundamentally the mean or the central value. And what standard deviation gives you, it gives you the measure of spread. This is what your standard deviation gives you. It basically how far away from the mean the points lie in a normal curve. That is what the standard deviation indicates. So there can be two curves like this that can have the same spread, but they can have different means like this. These are two normal shaped curves. Now, they are, all these diagrams are not drawn to scale, but the fundamental idea that I'm trying to say is that their spread might be the same. However, their means can be different. This is mu1, this is mu2. Adding to that, there can be also another case where you will have the exact opposite. You will have two curves to draw this a little better. Yep. So here in this case, if you can see, the mean of both these curves is the same. But if you look at their spread, this is a much more narrower curve compared to this, where the spread is much higher than the first case. So these are the two scenarios where I explained you what the mean and standard deviation in a normal distribution represent. To reiterate, the mean represents the central value of the distribution, and the standard deviation is a measure of the spread or how far the points are from the central value or the mean. Now, coming to a very important and recurring property of normal distribution or the bell curve is the 68, 95, and 99.7 property, or what statisticians also call the 68, 95, and 99.7 rule. So all in all, what they're saying is that 68% of all values which are part of the normal distribution, they lie within one standard deviation from the mean value. 95% of all values lie within two standard deviations, and 99.7% of all values lie within three standard deviations. So to explain this in a little bit more detail, what it's fundamentally trying to say is that if this is my mean, mu, and this is mu plus sigma, and this is mu minus sigma, the area under the curve, this complete normal distribution, if you consider it as 100%, which is the complete area under my normal distribution. So this particular area, which I'll be highlighting in a different color, let me pick up yellow. This area right here, this is 68%. Okay, so 68% of all values lie between or lie within one standard deviation from the mean value. And so one standard deviation towards the right and one standard deviation towards the left. This is the complete distance in which your 68% of the data lies. Similarly, if you take the same bell curve, this is my central value mu. And if you go a little further, and this time you go two standard deviations from the central value, now this area, if my complete area is 100%, this right here is 95%. All right. And similarly, if you go three standard deviations on either side, the total area in between will be 99.7%. So to reiterate what I told you in the beginning of the video is this is the exact precise thing that statisticians found out, that majority of the data points lie between two extremities which are more or less close to the close to the center of the complete distribution. So I'll remove this. So the next question is, do you have to memorize this fact that, okay, 68% of the values lie between one standard deviation from the mean, 95% lies within two standard deviation, and 99.7% lie within three standard deviation? The answer to this question is not really. And in the upcoming videos, you will understand this. And once you understand it programmatically, you will no longer feel the need to memorize this. Now we'll finish off this particular lecture with an example. Now, this is a sample question which we'll discuss in this video. The question says, let's assume that the distribution of the birth weight is normally distributed with a mean of 3,500 grams and with a standard deviation of 500 grams. So they have already given you the normal distribution. I'll redraw this. And this time I'll try and make sure that I draw it a little bigger so that we have a little more space. Okay, this right here is 3,500. I'll just remove this. I'll write it here so that it will be easier for you to understand. And your standard deviation is 500 grams. So for now, we'll apply our 68, 95, 99.7 rule over here. And we'll say that 68% of the data lie within one standard deviation from the mean, which means they lie between 3,000 and 4,000. %, between 2,500 . 500 and 4,500. How did we get this? 3,500 minus twice into 500, which is 1,000. And if you want to check for 99.7, this will come out to be, if you subtract 1,500 from 3,500, you will get 2,000. And you will get 5,000. Move this a little bit over. Yeah. So, all in all, this is what the equation looks like. This is derived completely from the 68, 90, 95, 99.7 rule. And so the question asks, what proportion of infants weigh between 3,000 and 4,000? You know the answer, it's 68%. What proportion between What proportion weigh between 2,500 and 4,500? You know the answer, 95%. And what percentage weigh more than 4,000 grams? This is an interesting question. I'll keep this transfixed over here, but I'll move up into my distribution. So now what we know is that 68% of data lies between 3,000 and 4,000. This is 68%. And another property of normal distribution is that normal distribution is perfectly symmetrical, which means that the right side is identical to the left side. So if this complete region, which I'll be marking in yellow, if this complete region is 68%, then towards the left and towards the right, the percentages have to be the same. So 68 divided by 2, we get 34. So 34 on the right, 34 on the left. And if you look at the mean, which is 3,500, then towards the left of the mean and towards the right of the mean, you can, from basic understanding, you can say that towards the left of my mean, there's 50% of the data, and towards the right of the mean, there is 50% of the data, which also follows from the symmetric property of normal distribution. So I'll add another highlighter. Preferably I'll take blue. So this right here, this complete thing, which is towards the left, which is marked in blue, this is 50%. So the question is what percentage weigh more than 4,000? So what is the area in question? The area in question is this that I'm marking in pink. All right. This is my area in question. So this right here towards the left marked in blue, this is 50%. This area that I'm marking in green, right here, This is 34%. So 50 and 34, this complete region is 84%. And we know that the complete area is 100%. So the answer to the third question is nothing but 100 minus the area towards the left, which is 84, and this gives you 16%. This third part might be a little new. The rest of the two parts of this question were pretty straightforward. So if you have some doubt, I would request you to rewind this particular video and watch what I've explained once again, but I'll just reiterate what I just said. So between 3000 and 4000, we have 68% of the data. Normal distribution has a feature of symmetry. It means that towards the right and towards the left, there is equal proportion of data. Towards the center, we have the mean. So to the right of mean, we'll have 50% of the data, and towards the left of the mean, we'll also have 50% of the data. Now, between 3000 and 4000, there is 68%. So between 3000 and 3500, there will be 34%, and between 3500 and 4000, there will be 34%. So behind 3500, there is 50% of the data, and behind 4000, there is 50% plus 34%, which is 84% of the data. So how far will be more than 4000? It will be the total, that is 100 minus 50 plus 34, which is 84. 100 minus 84 gives you 16. So 16% of the data lies ahead of 4000. We'll end the lecture here. In the next video, we will start with our second topic, which is standard normal distribution. Thank you so much, everyone, for watching.